Okay, assalamualaikum and good morning, everyone. So today we'll continue with our lectures. So let me go to my notes. I hope you are seeing my screen. Can you see this notes? Please say yes or no. Okay, great. So I think the last thing that we did was look at simultaneous linear equations, and let me just go back a little bit. So we come to the point of being able to determine, given the, say, let me go back further up, we can determine whether a set of linear equations can be solved or not by looking at the rank. I just wanted to show the augmented. Yeah. So we have this matrix M, and then we have this augmented matrix. So one can actually find the rank of this. So how to find the rank is essentially you do the row reduction process until you get to the point of probably finding that you cannot do any more row reduction because it's already in a either you have a row of zeros, or no, it's already in the canonical form which has the one along the diagonals. Okay, so if one can actually count the number of non-zero rows, that will be the rank of the matrix. Okay, so I think that's where we stop, if I'm not mistaken. So the summary is over here. So if you have your rank M less than rank A is, remember, the matrix, then you'll find that's inconsistent equations. So there will be no solutions if rank M equals to rank A equals to the number of unknowns. Okay, then you have a unique solution. If the rank is equal but not equals to the number of unknowns, then you have infinite solutions. So one can actually test this immediately, and then we will be able to conclude about the solutions of the simultaneous linear equations. So today we're going to go into a different topic called determinants. We have seen how determinants actually help you solve linear equations. We started off with, say, two linear equations given some coefficients A, B, C, and D, and then the right hand side is given by some numbers M and N. Then one can actually solve this by using matrices. Okay, your coefficients of X and Y is written as a matrix M. And when you look at the solutions, when we did all this using elimination of variables, then you find that you have these solutions, okay, for X and Y. And the thing that you have at the denominator here is essentially the determinant of your matrix M. So in other words, crucial to the finding the solutions are determining what is the determinant of that particular matrix M, which is the matrix of coefficients multiplying the variables. Okay, so once you know how to do that, so if your determinant M is not zero, then you'll be able to actually write your solutions in terms of this matrix equation. So we need to understand a little bit the idea of determinant. You know how to do this for the case of your 2 by 2 matrix. It's just AD minus BC. And you also know that, okay, the inverse of the matrix is related, uses the fact that you have the determinant here in the denominator. Okay, and then you change that. These are things that you already know in high school, but we want to generalize this idea, this technique, into a much more general technique. Uh, uh, I think probably what you see in BOAS is most probably just the numerical examples. So what I'm going to show you is probably a little bit more so that you understand the theory behind it. Okay. So suppose you have a n by n matrix. There is this procedure called the Laplace expansion. Okay. So this Laplace expansion will be able to help you determine the determinant. Okay. So what does it do? If you have already done determinant for matrices bigger than 2 by 2, then you know that what you do is essentially to use you take the original matrix, say 3 by 3, and then you reduce it to a 2 by 2 matrix and find the determinant of 2 by 2 matrix. Okay, so the whole procedure could be put into a much more general theory. So one has to learn about all this. It's called minors, for example. Given the ijth element, so you take the matrix M, so the matrix M earlier given by these numbers here, M11, M12. So you take the general element here, Mij. So the minor of the ijth element is essentially crossing out, okay, the ith row. Okay, remember the first index over here. Can you see? Let me just check. Can you see my cursor? Anyone? Yeah. Okay. Great. Because I'm not sure. That sometimes my cursor doesn't appear on your screen. So I'll do both. So here's hopefully this thing works. So the first index, remember, is corresponding to the row index. The second index is the column index. So the minor of the ijth element are essentially you cross out the I and you cross out the jth column. Okay. So that is called the minor. So the resultant matrix, okay, is written in terms of this notation M bracket ij, which is a matrix element which is which is a matrix which is n by minus n minus 1 times n minus 1 matrix. Okay, so that matrix, okay, with this bracket ij, so one should not be confused this as an element here. This is referring to the crossing out of your ith row and your jth column. Okay, so it's just a notation. Okay, so in other words, this is n minus 1 by n minus 1 matrix. Okay, and it's called a minor for the ijth element. And what one needs is to find what we call the signed minor. Okay, so when we do the determinant of 3 by 3 matrix, you actually, it depends on where the elements where you want to cross out. Okay, the sign of the element matters. So here the sign minor is just taking the coefficient over here of minus 1 of I plus j. So for example, in the case of a 3 by 3, for example, then you know, for example, if I have that, then if I expand about this row, for example, then I will have the first, remember that this becomes, let me just put some symbols here. Let me see, A, B, C. So the determinant of that, for example, you know that this equals to A times the smaller determinant, and then you carry on. The second one is a minus sign, and the third one is a plus sign. So how do you determine this plus or minus? Well, in this case, it's a 1 1 element. Your A is a 1 1 element, so minus 1 to the 1 plus 1 is just 1. And then the next one will be minus 1. So this is a 1 2 element, so it's 1 plus 2, so it's an odd number there. Minus 1 to the odd number is a minus sign, and so on and so forth. But now this technique is not just limited to the 3 by 3, but you can expand it to the case of n by n matrix. So what one has, okay, the minor is the n minus 1 by n minus 1 matrix. With the sign minor, we get what we call the cofactor matrix. Okay, so the cofactor matrix is also n minus 1 by n minus 1 matrix. Okay, so the determinant will be defined in terms of the element that you choose. For example, here I'm choosing the first row, so I'll choose here in the case of a kth row. So kth is determined, k is specified. So it doesn't have to be the first row or second. Well, you can take the second or third row, for example. So, here I'm taking a general case, the kth row. So you take the element in the kth row, okay, multiply with elements of your cofactor matrix. Okay. And your cofactor matrix, remember, it has all this plus or minus sign. So this would actually give you the formula for your determinant. It is slightly more complicated. That's why I said earlier it's a bit nonlinear in the sense of, when you implement in terms of operations on computer, determinant is harder to do. But here we have an algorithm in a way to determine your determinant in a much more recursive way. Okay, and one could also, as you probably have learned before, instead of using rows, you could also use columns. So normally, the way we, because the way we write, we tend to use row more, but one could use the columns instead. For example, over here, let's say this is D and E, then I could have done this for D over here and E here, for example. Okay, so it doesn't matter which one that you started with. Okay, you can use any row, or you can use any column for that matter. But you need one reference for which you do the expansion. So that's why it's called the Laplace expansion. Okay, you have that. So you need to be able to have a reference row or reference column in that sense. So let's just do an example so that you can actually see what's going on. Here is a 3 by 3 matrix. And I could have done a 4 by 4 matrix, but no. Let's make it simple. So here your M11, for example, is 3, M12 is 5, and so on. Okay, so you can see that from here, the first row, 3, 5, 1, and I'm going to use that row, for example, over here. Then I'll choose M11 equals to 3, M12 equals 5, and M13 equals to 1. So once you choose those elements in the first row, then you can calculate your minor or your you straightforward go into the cofactors. So here's the element of cofactor. So you have C11, which correspond to the minor of M11 with the sign. what's the minor of M11 is to remember you take the determinant of the smaller matrix. In this case will be a 2 by 2 matrix for which you know how to do it. Okay, so you take 0 times 4 minus 3 times 1, so that gives you minus 3. Okay, now if here you immediately get your numbers, but if you have chosen the example to be a 4 by 4, then you probably need to do the next step. You probably get a 3 by 3 matrix over here, and you need to take the determinant of that. Okay, so but here we just use the 3 by 3 example, so that you get immediately you get the values without further trying to expand the determinant over here. Okay, so let's move on and then look at M12. So M12 is this one, remember. So I'm going to cross out that, and I'm going to cross out that. So let's just cross out for a moment. Okay, so I'll have sorry, I'm crossing out the wrong row. I'm crossing out this column. I'm crossing out this one. So I'll get 2374, which is the one that appears in this determinant here. And I remember that M12, you have minus 1, 1 plus 2, it will be minus 1, so that you get the minus sign here. Okay, and then again, you know how to do the 2 by 2 determinant, so that will be easy enough. 2 times 4 is 8, and then minus 21, but remember you have a minus sign in front, so you flip that and you get the value 13, and the same thing for the next one. Okay, so here is M13. Okay, if I want to continue, I could have continued also with the rest of the rows. Here is the case of M21, M22, okay, M23. Do I really need that for the determinant? Maybe not. Okay, but it'll be good just to check later on that you'll have the same the same value for your determinant if you choose a different row. Okay, so here I'm calculating all the possible rows. Okay, so in this particular case, second row is given by this 3, third row will be given by that, the last 3. So if I ask you to do okay, give me the cofactor matrix, then you probably need to do all the rows, for example. Okay, so here's the cofactor matrix being calculated out before. Okay, let's look at it. Okay, here's minus 3, 13, 2 for the first column, first row. So we just look, minus 3, 13, 2 is that, and then the second row would be this 3, 19, 15, 32, and that is 15, sorry, I probably make mistake here. That's 12 minus 7, that's a 5. I do not know how to do arithmetic anymore, so that's a 5. Okay, so that's a 5 there. So you probably want to check the notes as well. Okay, so that will be a minus 19,532 there, and then the last 3 would be 15 minus 7 minus 10. Okay, and what one needs for the determinant is to be able to choose any of the rows. So you don't have to really, if you are not asked to find the cofactor matrix, you don't need to find all the elements there. You probably just need to stop at the first row. Okay, so in this case, I can use the first row, for example. Okay, then I'll be able to multiply the elements here. M11 is 3 and C11 is minus 3. M12 is 5 and C12 is 13 and M13 is 1 and C13 is 2. And then you add those up and that precisely gives you the determinant of that matrix M earlier. Okay. So now I want you to do some exercises for me. One could start doing different things. Oops. What am I don't want to do any shopping today. Okay. So one can check if you start to use a different row, for example. Okay, maybe as an exercise, do this for two cases. Determinant M by expanding about the second row M21 C21 plus M22 C22 plus M23 C23. Okay, check the number. It should be the same as the number 58 over here. And then this is one. See, the other one is to use a column. So let's use a column. In that sense, I will need something like this. Let's use the second column. So I have M12, C12, M22, C22 plus M32, C32. And please try to do this and check that you get the same number. Okay. So that's why I said earlier just now, I could have stopped with the first row and not use the other rows. Okay. So I don't need the other rows, in fact, unless I'm being asked to calculate the cofactor matrix. Okay, which is a possible question. Okay. In this case, then you need to do every row or every column, whatever. Okay. Right. There are some useful things that you should know about determinants. If one of the row or one of the column for the matrix is multiplied by a number k, for example, then your determinant becomes multiplied by k of the suppose you have the determinant m before, then with this new matrix by multiplying k to one row, remember it's only one row, in this particular case, then you have a determinant to be multiplied by k. Suppose I have something like this. Let's take the 3 by 3 case again. So we have a 3 by 3, and this is m, and then I'll multiply the whole matrix by k. What do you think will happen? What would be the determinant of k times m? Can anyone guess? If only one row is multiplied by k, it gives you the determinant multiplied by k. But if all the rows are multiplied, so what do you think will happen? So let's fix to the case of M is a 3 by 3 matrix. Anyone can guess? maybe no, this type of question I would like to do this as a quiz, perhaps later on when I have time to do this, as a quiz inside your Putra Plus. Okay, so you should be able to answer that. Okay, if you don't answer now, you probably have to answer this later on. Okay, so what happens is that it gets multiplied. In this case, since you have a 3 row, that means you have a k cube multiplying your determinant. Okay, so okay, anyway, so what are the properties of the determinant that you should know is the fact that if one row or column is going to be all zeros, okay, then you know definitely the value of your determinant is going to be 0. For example, suppose I'm asked to find the determinant of this matrix A 0, B, C 0, D, E 0, F. Now, if you do the expansion about this column, then you know that 0 will multiply everything. Okay, so in other words, then you have your determinant to be equal to 0. The other one will be if you have 2 rows are identical or 2 columns are identical, you also get your determinant to be equal to 0. This is a bit less obvious to actually show, but it corresponds to the symmetries that are actually available when you do determinants. Okay, let me just do this first. The 2 rows are identical, then you have determinant 0, or the 2 rows are proportional, even proportional case. Okay, you also get your determinant to be equal to 0. Now, why is this happening? It's because you already know that when you interchange 2 rows or 2 columns, your determinant will change sign. Okay, why does it change sign? Because remember, when you do the cofactor, you always have this thing. So if you start swapping things around, then you're going to swap some of the minus sign around. Okay, so that's why you have this determinant to change sign if you have 2 rows being interchanged. And that will also explain why you have this property when 2 rows are identical. When you swap the 2 rows, you're supposed to get a minus sign, but they are identical. Then you get something like some number like alpha equals to minus alpha, but then that will tell you 2 alpha equals 0. So in other words, your alpha is just 0. Okay, so same thing with the columns. Okay, the proportionality is a bit more involved because it corresponds. It really, I should say that it connects to the idea of elementary row reduction. Okay? Because in elementary row reduction, what you can try to do is to make multiply a particular row and then make linear combinations with the other. Okay, but okay, let me just tell you the properties just in that sense first, so that you know that one of the things that you can try to do with all these facts is that you don't need to do the calculation unnecessarily. Okay? Once you observe, for example, this matrix, then you know that your determinant is actually 0. And then here is the thing that I'm supposed to, okay, perhaps the wrong way around to write this. Okay, the determinant is unchanged if the rows are written as columns. So you swap the columns and rows. Okay, and then the one that's supposed to explain this one is this one. You add element of one row with corresponding elements of another row multiplied by a constant. That also will not change the determinant. Okay, so and then finally the determinant of a product two matrices, then basically that gives you the answers to be the determinant of the individual matrix multiplied together. Okay. Again, one can prove this if you want to, but again, the theory is a bit involved. That's why theory of determinants is a little bit more sophisticated than just your ordinary cases. Okay, what is this? Okay, oh yeah. So again, as I said, there's this property of determinant. Please take note, this is not quite inside your Boas book, so I'm teaching you some extra thing, okay, that happens behind the scenes, so to speak. You know, there's no, if you swap two rows, then you get negative sign. So you have this idea of an empty symmetry, okay, meaning you change rows or you change columns, you get a minus sign. Okay, so how can we actually encode this in a much more compact way is to introduce this idea. So I'm going to jump ahead instead of going through all the text over here. You can read for yourself. I'm going to introduce this idea of a Levi-Civita symbol. Again, this is not necessarily the thing that you're going to get inside your Boas book, but it helps you to think a bit more general than what, no, just numerical calculations. I put, okay, probably, no, my philosophy over here is that when you come to at the high school level, for example, high school level, you are given formulas and then you substitute numbers inside it and then you get answers out. At the bachelor level, you are supposed to know why that thing works. So that's why I'm teaching you all this, okay? So here is a symbol, just like you remember I introduced the Kronecker symbol, okay? So the Kronecker symbol helps you to define scalar product for vectors. And what's the other one that I mentioned earlier? Or the trace of a matrix. Okay, so we have already introduced something new. I did ask whether you have learned this, and everyone seems to say no. So I'm definitely sure that you have not seen this, right? Maybe I should hear some answers. Have you seen epsilon ijk before? Okay, so it's a new thing, but no, I hope no, you don't get turned off by these new things. You're supposed to learn new things, not just reiterate old things. Okay, so what is this epsilon ijk? Just like your delta ij was actually given as 1 or 0 if I equals to j is 1, if I is not equals to j it's 0. You have a similar kind of thing happening here where your epsilon ijk is going to be either 1 or minus 1 or 0. Okay, so you have this additional thing minus 1 here. Okay, when is it equals to plus 1 is when your ijk is an even permutation of 1, 2, 3. Now, what do I mean by that? Suppose I have something like 231, epsilon 231. So what is the value of epsilon 231? So I will look at 231 is not in the natural order, right? So I need to do what we call swapping the numbers around. So I swap the first time, say I will swap between 3 and 1, I will get 2, 1, 3, right? And it's still not in the natural order. So I swap another one, which is 2 and 1 over here, and I'll get back to the natural order. Okay, so how many swaps are there? Okay, you're supposed to say something. How many swaps are there? Well, nobody is listening. 2. And 2 is an even number. So in other words, epsilon 231 is a plus 1. Okay, so let's do another one. Let's do, say, epsilon 321. Okay, so let's swap the numbers around. So let's do 312 and then 132 and then 123, right? So how many swaps are there? 3. And 3 is an odd number. Okay, so now the epsilon 3 to 1 is minus 1. And if you have the other case would be epsilon, say, 331. Here you can't do anything to get the natural ordering, so it's the otherwise case. So epsilon 331 is just 0. So if you have, for example, any repeated number into the index of the epsilon, then it's going to be equal to 0. So why are we learning this? Is to be able to write your determinant in a very compact form in this way. So here is the case of a 3 by 3 matrix. Okay, you can check for yourself. I'm going to expand your determinant in terms of this epsilon ijk, and here I'm writing the elements of your matrix M1I, M2J, M3K, and this indices ijk will have to be summed between the numbers 1 and 2 and 3. So you have to expand this thing, and this is just the same expansion that you see when you do the Laplace expansion. So I have what? So I start expanding, so I'm just going to write down what they are, and I'm going to omit the case where you have index which are the same. For example, 331. So I ignore all those. So I only look for indices where they are all different. So I will have epsilon 123, epsilon 231, epsilon 312, epsilon 321, epsilon 132, and epsilon 213. And then the numbers over here just follow the indices. Okay. And then if you check what they are, then you see that, okay, some of these numbers are going to be negative. This one I've chosen in such a way that this is negative, this is negative, this is negative. So I get that. Okay. And then you combine, for example, if I want to show that this is a Laplace expansion about the first row, then I choose the first element M11 and the second element M12 and M13, okay, and then collect all the factors that that is multiplied by M11, M12, and M13, and you'll see that this is precisely the right expression for the determinant using using the first row of M. I could have collected this differently if I want to. I can think of this as instead of first row. Okay, I could have done this. Okay, let's collect the case of the second row. Then I look for numbers M21, M22, and M23, and then you get a different result. But no, they all come from the same thing. It's just this thing. So now it doesn't really matter in a way. You have this formula that no sort of irrespective what reference row or reference column that you use, it gives you all these same numbers, but you can recollect them in a way that okay, this is actually determinant by with reference to the first row, for example. Okay, but they are all the same. Okay, so again, I believe these are not being taught to you in general, so that's why you probably, and you can also prove then over here that why certain what you call why certain properties of the determinant before, for example, when is it 0, you can actually determine from these properties of your expansion here. Okay, again, this is just the theoretical part. When you do calculation with specific numbers, you do it, I mean, without worrying about all this epsilon thing. But if you are doing it with the case of a symbolic, instead of numbers, you have the matrices having symbolic, sometimes it's much better to do it this way. Okay, and the other thing about that, okay, I'm going to jump straight over here because I know this is not really part of what you're going to learn in BOAS. You can generalize it to any bigger matrix, n by n matrix. Okay, so there what we need is a generalization of your epsilon symbol earlier. Instead of having 3, which is meant for a 3 by 3 matrix, here you have your index over here will have n of them. And how do you find whether it's +1 or -1 or 0? It's just the same thing. If your ordering of over here is not the natural order, then you have to permute them, and then you find whether it's an even permutation or it's an odd permutation. Okay. So so generally we have the formula of your determinant given by this formula. Okay. So I will probably not carry on further because some of these are just reproducing what the things I mentioned before. Okay, so you can have a read if you want to understand the theory behind it. So I will stop there for this lecture. Probably I will just have a glimpse of the next one. Okay, the next one we are going to talk about Kramer's rule. Okay, so Kramer's rule, you probably have learned this for the case of two simultaneous equations. We're going to generalize this. Okay, so if you have done Kramer's rule before, may I ask, have you actually seen Kramer's rule before? Anyone? Great. It is usually two simultaneous linear equation, right? If it's bigger, you probably if you have done a much more advanced topic, then probably you have seen a bit bigger than that. But the idea is the Kramer's rule tells us how to determine the solutions using determinants. So again, the idea of determinant is going to be important for us, and I'm going to just give you a glimpse before we do it in the next lecture. You can actually generalize to the n simultaneous linear equations, and then again you have an analog of the Kramer's solution, of Kramer's method, for the case of the two simultaneous linear equation to the case of the general case. So I think what else do I want to do? And then once we have done that, we look again under what you call inverses and probably learn a little bit more Again, determinant is going to be there. Finally, for the next one would be, I think, yeah, okay. The other one would be the idea of special matrices that correspond to some physical transformation. One of the things that we're going to look at is essentially rotation matrix. Okay, we'll do this, no, the next lecture, not now. I'm just giving you a glimpse of it. And finally, what we're going to do is a generalization of the rotation matrix involving complex numbers. Okay, and then we talk about of all the different types of matrices that you can have when you have complex numbers as your entries of your matrix. So I will stop here today. So it's less than an hour, but I thought this would be a nice place to stop. Any questions so far? I believe I put up notes on the Putra Blast. For your assignment, please try to do this before. Do you want a deadline for Saturday? What time? Any suggestion you can put on the chat? Can 12 a.m. 12 midnight. So that means just bordering between Saturday and Sunday. We have agreed on 12 p.m. Yeah, I thought I mentioned something about that. So 12 p.m. Is that okay? If you need extension beyond 12 p.m. on Saturday, just let me know. No, and then I'll open it up. So it depends on your progress. Again, the idea of doing this in groups of two is to help you share the problem solving. Okay, and no, you need to be able to experience yourself how to solve some things. Okay, and then you can discuss among each other about your own solutions. Okay, the test would be chapter 1 and chapter 2. That means lectures 1 to 4. I think it's going to be the series, and it's going to be the complex numbers. Okay, anything else? So probably I will take the attendance now. So any questions about the assignment or what do you call assignment or the first test? The first test will be on Monday. Okay, so that means I need to get your solutions up before that so that you have a reference to see. Okay, no questions? Everyone's cool? Understood everything? Okay, if so, then let me end the meeting. So thank you, everyone. Okay, bye.
Thank you.